Yeah, I know, I hate shapes.
Complex numbers. What is a complex number? Anybody remember? I know. I always laugh at, like, whoever came up with the name of this. Like, could you maybe, like, help out us math teachers a little bit, right? Like, complex numbers or complex fractions. Like, why do we have to call it complex? Can we come up with some other name? Because as soon as I put complex numbers up here, everybody's like, oh boy, this is going to be hard, right? This is complex. Today is complex numbers, which is in the form of a plus bi. And so what do we notice? We have an I, which means we are now into imaginary numbers. Okay, so now we're not just in the real number system. Now we are throwing imaginaries back into the mix. And so now when I see the square root of a negative, I can do the square root of a negative because we now have imaginary numbers. So we're going to kind of review what imaginary numbers are, because I know you hit this topic pretty heavily. I just went into Mr. Moeller's room, and they're in complex and imaginary numbers in Algebra 2 right now. So it is something that you've had a lot of prior knowledge of. Probably the biggest thing that's different between Algebra 2 and college algebra, and we've talked about this in a lot of different scenarios, is everything that we're going to cover today, you probably covered in about 3, 4, 5 sections in Algebra 2, and it's all going to be loaded into one big section today, because we're going to do operations with complex numbers, and we're going to do a lot of different things with those complex numbers. Okay, so what is a complex number? A complex number is a number that is made up of a real part plus an imaginary part. And we always write it in this format, a plus bi. So an example of a complex number would be 3 plus 2i. Typically, like slope-intercept form, we always do like 2x plus 3, right? And when we always put the x in front, because that's what we call standard form of a polynomial. But when we do complex numbers, the imaginary part always comes last. It's just the way we always write it. So it's a little bit different in the format that we write it in. And it's not necessarily wrong if you were to write it as 2i plus 3, okay? But that's not the format we're going to see it in, so a lot of times we're always going to end up with the i being the last thing that we're going to talk about. Okay, I could also give you a number like 8i, right? 8i is still a complex number. It just doesn't have a real part. So what do you think the real part would be that's attached to this? 0, yeah. Because this would be the same thing as saying 0 plus 8i. We just don't need to put the 0 there because anything plus 0 is still itself. So we usually just write it as 8i. So it's still a complex number. We just don't put the 0 there with it. And so a lot of times you will see a number that's 8i all by itself or 2i or something like that. And we just leave it as 8i. So what is I? Well, the definition of I is the square root of negative 1. Because in the past, the last 2 chapters, we've said if we had the square root of a negative, we couldn't do anything. We would say, not possible, no real solution. Well, now that we have imaginary numbers, we are able to find a solution for it. And there's sometimes where we go from an imaginary set and we end up my answer as being a whole number, okay? And so we'll be doing a lot of going back and forth. There are some jobs, more like engineering type jobs, that you deal with I's every day. I always kind of remember, like, it's probably been 10 years ago now, but I ran into a former student at Dillon's, like over Christmas break. And he had just graduated from K-State, and he was working at I don't even remember what the place is in Kansas City. He had gotten a job, and he was doing engineering, and he's like, I got a story for you, Mr. Ruda. And he told me how he uses imaginary numbers every day in his job, like whatever the work was. And I said, hey, that's great to know, because now he tried to explain to me exactly what he did, and I can't probably tell you exactly what he was telling me, but he was in like some type of like chemical engineering, I think, and so he was using imaginary numbers every day. So there are some jobs that use imaginary numbers in their data or in their things that they do every day. Do most jobs use imaginary numbers? Probably not, right? But there are some out there. Maybe you guys will be the one that uses imaginary numbers in your job. Sounds like fun, right, McCade? You're not going with that? No? All right, so here's what we're going to do. We're going to talk about why we would maybe need imaginary or where we can use it. If I were to give you the square root of -7, okay? Last chapter, we would have said, we can't do this, no real solution, right? Well, now we're going to split this up. We're going to break it up. And whenever I have a negative, I'm going to break it up into -1 and the number, okay? And what we really know now is the square root of -1 has now become I. I can't do anything with the 7, so we just leave the 7 underneath. And so our simplified result would be I radical 7. And that's our answer. Okay? And unfortunately, you're not going to just be able to put these into your calculator, right? If you tried taking the square root of -16 in your calculator is going to say no real solution or not possible, non-real. Every calculator is a little bit different on how it expresses it. But there is an answer here today. So when I see that negative, I'm going to break this up into -1 times 16. Now this one's a little bit different because the square root of -1 is still going to give me the I. The square root of 16 is 4, right? So this would simplify to be 4i. And we don't have anything under the radical that's left. If I put a negative in front of the radical, it doesn't change things much. It just means in my final answer, I'm probably going to have a negative on my answer. It just stays out in front along with everything else. As you do this more and more, and because you've kind of done this before, you probably are going to be a little bit better, hopefully, at it than what you were even last year. But I always like to rewrite it, okay? And like I said, as you become better at it, maybe you don't need to rewrite that every single time, but just knowing why and where it comes from, this -1 is coming out of the radical, and it's becoming an I. So this would become -I radical 13. And so that negative doesn't go anywhere. It just stays out there in front. The I is the only thing that comes out. And basically what we've done is we've gotten rid of the negative underneath the radical, and now it's a number that we can do. Okay, one last one with simplifying radicals. If I were to say the square root of -48. There's a couple of different ways that you can approach this one. First thing I'm going to do is I'm going to break it up in -1 times 48. Now, depending on what method you like the best, okay, there's two ways that you can do this 48. 48 is not a perfect square. You remember your numbers like 16, 25, 49, 64, and things like that. Those are your perfect squares. 48 is not one of those numbers, okay? But if you remember back to your days of simplifying radicals, I can break this 48 down. And there's a couple different ways we could do that. You could do the tree, where you could take 48 and you could find the prime factorization. Okay, anything that goes into 48 would be like 6 and 8. And then I keep breaking it down into 2 and 3, 2 and 4, and then 4 breaks up into 2 and 2. Okay, but what I like to do instead, and especially because we're in college algebra now, and maybe we have a little bit better number sense, hopefully, then we just think of our perfect squares, right? And so our perfect squares, like I mentioned before, 1, 4, 9, 16, 25, 36. And you should be able to identify the first 10 perfect squares pretty easily. When I see these 10 numbers, I should immediately know that's a perfect square, especially for this chapter when we're dealing with radicals, okay? And we're going to see radicals a lot. And so what I'm going to do here is I'm going to find that one of these numbers that goes into 48. Well, 4 goes in there. Yep. 9 does not go in there. 16 does, okay? 25 doesn't. And so we're going to take out the biggest perfect square that we can. And so the way I like to do this one is rewrite this as -1 times 16 times 3. Okay? Because 16 is the biggest perfect square that goes into 48. Okay? Now, when I take out the square root of -1, what's it become? I. Okay? When I take out the square root of 16, what's it become? 4. Okay? So this becomes I. This becomes 4. So this becomes 4I radical 3. If you would have done it this way, and I'm going to show you this way also. We have 4 2s and a 3. You guys kind of remember doing it this way too, with the factor tree and the prime factorization? We're looking for pairs. What do I have pairs of when I do that? You don't need a pair for -1, but we have 2 pairs of 2s, right? So we're going to bring out this 2. We're going to bring out this 2. And 2 times 2 becomes 4I radical 3. Okay? And that's why I kind of like this one better, because this gets a little bit messy, I think. There's a lot of stuff going in it. Like, if you guys had to choose, how many would rather do the tree diagram? Anybody like that still? And if you do, it's okay. Like, and I'm showing it to you, right? If you're, and it probably kind of goes back to how you learned it or taught it or used it the most, okay? But I'm showing you this method here too, because if you can find a perfect square that goes into it, I think it's a little bit less work, okay? Both of them get us to the same result. 4I radical 3 is where we want to end up. Okay, another thing that you're going to see, and this is going to be towards the end of your assignment today, are your powers of I. And there's 4 powers of I that we have to remember what the result is. And then I'm going to show you some examples that will use this and how we can come up with it. I to the first is I. Anything raised to the first power is itself, okay? And that's the same thing as the square root of -1, if you want to think of it like that. But you're going to have some problems today where it's going to give you like I raised to a power, and you have to tell me what the result is going to be. I squared. Well, I is really the square root of -1. So if I take the square root of -1 times the square root of -1, when I take a square root or a square root times itself, the square root disappears. So I squared is really -1. Okay? And I'm going to put a big star by this one because this is one that we have to know. We're going to see this happen over and over and over again throughout this chapter. Okay? And whenever I see an I squared, I'm immediately going to change that to a -1. We never ever want to leave an answer with an I squared in it. Okay? So that's really the big one out of these powers of I. I squared is equal to -1. Got to know that. Okay? I to the third. Okay? Now, I to the third, I could rewrite it as like I to the second times I to the first, because 2 and 1 make 3, right? And when we multiply a power, and when we multiply two things, we add the powers. Well, I squared is really -1. I to the first is I, so I to the third is really -I. Okay, and then finally, I to the fourth. I to the fourth can be thought of as I squared times I squared. But I squared is really -1. And so when I take -1 times -1, I really get 1. Okay, so those are your 4 powers of I. The big one is I squared, okay, but these are the ones that we have to know whenever I do a problem like this. I to the 43rd power. Okay. Now I'm gonna do a smaller one first, and then we'll do I to the 43rd. Let's say I do I to the 15th. If the number is smaller, if my power is smaller, then I could simply just count. So this goes 1, 2, 3, 4, and then we're going to start back because there's only 4 different values I have to remember. So then they would become 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I to the 15th would be the same as I to the 3rd, which is -I. Okay? And so we would say I to the 15th is -I. So that's one way you could get there. You could just count, right? As long as you know your power, your 4 powers of I, then you could just count. Now, I don't really know if I want to do that for 43, right? 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 43, that's going to be counting for a while. Or if I said I to the 82nd, don't want to count up to 82, right? Got better things to do than count to 82. So how do we do it if I go 43? Well, since we have a group of 4, okay, then we're going to find the number that's closest to 43 that divides by 4 evenly. Okay, what number is close to 43 that divides by 4 evenly? 40. Or what's even closer? 44. Yep. Okay, and you could do either one. Okay, I'm going to do I to the 44th. Okay, so anything that is a power of 4 is going to be the same as I to the 4. Okay, so 4, 8, 12, 16, 20, all the way up are going to be the same as I to the 4. So I to the 44th, because 44 divided by 4 is 11. It divides evenly. Okay, then that would be the same as I to the 4th. So I to the 43rd would be the one right before it, which is -I. Okay. If you want to count, you can count, but you can do it that way. You guys want to do another one of those? I to the 62nd. Does 62 divide by 4 evenly? Meaning I don't get a decimal. 62 divides by 4? No. Okay, so 62 does not divide by 4. Okay, so I could either go up or I could go down. So I could go up to 60 or I could go down to 64. Okay, either way would be fine. Okay, and I'm just going to show you all these. Okay, I to the 60th and I to the 64th are the same thing. They are the same as I to the 4th, right? Because they're both powers of 4 or multiples of 4. So this would be 1. And then I'm going to start over. And then this would be I. And then this would be -1. This would be -I. And then we're back to 1. Okay? So it doesn't matter if I go here and count backwards to 62, or if I go to 61 and count up to 62. In both cases, I'm going to be at 1, and I'm counting up, or I'm counting back. Okay. Any questions on that one? Those are a little bit tricky, and to be honest with you, you're not going to see a ton of those. Okay. I think we do have one like that, like on quiz or test. But we're not going to see a ton of those types of problems where we have I to the power. what we're going to focus on more today is all of our operations. Add, subtract, multiply, and divide. So we're going to have complex numbers with some type of operation within them, okay? And we're going to start with the real basic ones, add and subtract, and then we're going to work our way up to multiplication and finally division. Okay, so let's start with addition. You're going to have two complex numbers, and we're going to add them together. Okay, and here's what I'm going to tell you. Don't make it harder than it needs to be. This is just combining like terms. That's all it is. Treat i's just like you would an x or any type of variable, right? Because that's kind of really what it is. Even though it's a number, I is a number, we're going to treat it as a variable. So 8 plus 3 would be 11. 6i plus 2i is 8i. It's as easy as that. Okay? That's my answer. That's as simplified as I can get. And so that would be our simplified expression. Okay, for subtraction, the one thing I would warn you on this one, and we made this mistake a lot when we did function operations last chapter, this mistake was made a lot because we didn't write it out correctly. But if I'm taking this complex number minus this complex number, what do I have to do with this minus sign right here? Got to distribute it, okay? It has to be minus 6 minus a negative 3i. We have to distribute it to both parts of that second parenthesis. The first parenthesis, nothing happens. And probably wouldn't be a bad idea to even rewrite it. Minus 6 plus 3i. Because when I distribute, it's going to change signs. And then 4 minus 6 would become negative 2. 5i plus 3i would be 8i. And that would be our answer. Okay. So you just really got to watch your signs, combine like terms. Okay. Addition and subtraction is pretty straightforward. Multiplication. There's going to be several different types of multiplication we're going to look at here. Okay. First of all, sometimes we're going to see problems written like this. Okay. And here's what you cannot do, is we cannot multiply these two together and make this 10. Okay. Because right now this is an imaginary number. So we have to make it an imaginary number. Anytime I see a negative under the radical, I have to make that imaginary right away. Otherwise, we wouldn't be able to do anything with it, okay? So right away, I'm going to make this I radical 2. Kind of like we did at the beginning, where we took a negative out of the radical and leave the 2 inside. I'm going to make this one I radical 5. Now I can multiply. And when I multiply these two together, I times I would give me I squared. And now I can multiply the 2 and the 5 together, and that gives me radical 10. Oops, I don't know why I put an equal sign there. I squared radical 10. Okay, but then here's what we talked about just a few minutes ago. Anytime we see I squared from here on forward, anytime throughout this chapter, I squared is really what? Negative 1, okay? So we're really going to rewrite this as negative radical 10. Okay, you don't necessarily need a 1 there, because if there's no number there, it's assumed to be a 1. So we just make that negative radical 10. Okay, like I said before, you do not want to multiply these two together right from the start. That's the mistake a lot of people make, because they go, oh, well, negative 2 times negative 5 would be 10, so that really just becomes radical 10. It's not true, okay? It's not radical 10. We got the negative out there, so the negative would have to be part of my answer. if you multiplied them together at the beginning, then that would not get you to the right spot. Okay, if I gave you one like this, square root of negative 16 times the square root of negative 25. Square root of negative 16 really becomes what? 4i. Yep. Square root of negative 25 becomes 5i. So this becomes 20i squared. But what is I squared really? Negative 1. There it is again, right? And I always like to just kind of like write a negative 1 right there and cross out the I squared. And then 20 times negative 1 becomes negative 20. So notice how we went from a number that we couldn't do to a number that we're more familiar with, right? Even though it's negative, this is a real number. We started with imaginary numbers. So there's an example where we started with imaginaries, and now we're out of the imaginary set, and we're back to just a regular old number, negative 20. Okay? And that'll happen sometimes. So you do not have to have an I in your answer, right? Especially when you get I squared. You may not have an I in your final answer every single time. Okay, so that's one type of multiplication where you're just taking an imaginary number times another imaginary number. You may have to make it imaginary to begin with. Okay, here's another one. Hey, Mr. Patton. We're going to take a complex number. Thanks. No. Yep. So we have a binomial times a binomial, and we saw a little bit of this in the last chapter. When I have a bi times a bi, what are we going to get? Or what do we have to do, I should say? Foil it. Yep, it's good old FOIL. Okay, so we're going to FOIL this out. So we're going to do 1 times 1. 1 times 3i. 2i times 1. 2i times 3i would be 6i squared. Okay, so when we FOIL it, we'll get 4 separate terms. Now we're going to simplify it. 3i and 2i becomes 5i. There we see I squared again. Like I told you at the beginning, we're going to see I squared over and over and over again. We're going to see it a ton. Okay, and that's the one you got to know. You got to know that I squared is negative 1, and we can never leave our answer as 6i squared. We never want to leave an I squared in our final answer. And then I can combine 1 and minus 6. So this would be negative 5 plus 5i. And that would be our final answer. Okay, I'm going to show you some other variations that are a little bit different. Here's one that seems to get missed the most. 3 minus 7i squared. So we have a binomial in parentheses, and we're squaring it. And when we square something, we're really doing what? Foiling it, right? We're taking it times itself. Okay, so to be successful here, then I feel like the best way to do this one is to write it out. Okay, you could probably do it without writing it out in some cases, but I think that would be harder. So I would take the time to write it out because we're squaring it, so we're taking it times itself, and then it's just like the last problem. It's just a FOIL problem. So 3 times 3. 3 times negative 7i. Negative 7i times 3. And then negative 7i times negative 7i would be positive 49, because a negative times a negative makes a positive I squared. Okay, we're going to combine like terms. And once again, this is really -1, so it becomes -49. And then I can do one more step here. 9 minus 49 is -40 minus 42y. And that would be your answer. Okay, the last two multiplication problems I'm going to show you are very, very similar. But we're going to talk about the word conjugates. This is a word that we're going to see off and on throughout college algebra. So I want to talk about this word because we're going to see this word show up, and I think it's really important to know what this word means. And you probably heard or saw it in Algebra 2, but it's been a while, okay? Anybody remember what a conjugate is? If I said 5 plus 7i is my complex number, and I asked you for the conjugate of 5 plus 7i? 5 minus 7i, good. It is the same two terms. The only sign that gets changed is the sign in between the two. So this is 5 plus 7i, this becomes 5 minus 7i. These two are what we call conjugates, okay? And the reason why this is maybe just a little bit different than the ones we did just a second ago, it's still going to be a FOIL problem. So you might say, Mr. Rita, this is the same thing we just did. But I'm going to show you what happens when you multiply two conjugates together, okay? So we're going to FOIL this. And because these are conjugates, anytime we have conjugates, what's going to happen is the two middle terms are going to disappear. They cancel each other out. Negative 35 and positive 35 make 0. I squared, once again, is -1. So this becomes 25 plus 49. So once again, do we have to have i's in our answer every single time? Not necessarily, okay? It's not, don't freak out. If like, man, I got all these i's in this problem and my answer doesn't end up with an I. I think something's wrong. It's not, okay? And will you end up with i's a lot? Yeah. Do you have to? Not necessarily, okay? It all depends on what you have. One other example of conjugates, and this one's a little bit easier, would be 8i and -8i. Those two are conjugates. Remember we talked about at the beginning, it's really like putting a 0 in front. 0 plus 8i, 0 minus 8i, but we don't need the zeros there. So 8i and -8i are conjugates. And when I multiply these two together, I get -64i squared. But once again, we've seen it a bunch now. I squared is really -1. So this is really like taking -64 times -1, which ends up being 64. So conjugates, when you multiply two conjugates together, you will not end up with an I in your answer. Okay, that's why conjugates are different, and that's why I wanted to make sure you understand what that term is. And plus, we're going to use conjugates here in just a second, because the last problem we're going to do here is division. And there's only one type of division problem. Multiplication had some multiple ways of doing multiplication depending on what we had. For division, you're going to have a complex number divided by a complex number. Okay, what you cannot do, because this is a binomial and this is a binomial, you can't just like knock those i's out and make them disappear, right? If there was no plus or minus signs, then I could do that. But with plus or minus signs attaching things together, that makes that an entire expression or term, okay? So we can't just knock the i's out. So whenever we have division like this, we're going to multiply by the conjugate, another reason why I'm using that word again, of the denominator. On top and bottom. Okay, and the reason we do on both top and bottom is because we have to make it an equal expression, right? If I gave you a number like 1 over 8, and I say give me a fraction that's equivalent to 1 over 8, then I could multiply top and bottom by 2, and 2/16 would be equivalent, right? I can't just multiply the bottom or just multiply the top. I got to do it to both top and bottom. But here I'm doing it with a conjugate of the denominator. So the denominator is 1 minus 6i. So what would be the conjugate of the denominator? 1 plus 6i. Good. Okay. But I have to do that to both the top and the bottom. Okay. One thing I will tell you is do not change the sign on the 1. That's a common mistake a lot of people want to make. Only sign that changes is a sign in between. Do not change the sign on the 1 here. Okay, and what makes this a little bit harder is we basically have 2 FOIL problems here. Okay, so I don't think it's necessarily hard, it's just a little bit of work. Okay, we got to FOIL twice here. Okay, now the reason we do this is because we can't end up ever with an I in the denominator. Kind of like we never want to end up with 0 in the denominator, we never want I in the denominator. And when I multiply this by its conjugate, that's going to get rid of the I out of the denominator. So I'm going to go ahead and make this plus 30. So this would become 32 plus 7i. On bottom, these two are going to cancel out. This becomes plus 36. So the denominator is now 37. Okay. The last thing that we're going to do here, just because this is the format that we always write complex numbers in, we always write it as a plus bi, right? We have a real part and we have an imaginary part. So to rewrite this, we're going to divide 32 by 37. That's my real number. And then we're going to divide 7i by 37. And that's my imaginary part. And now it's in that a plus bi form that we want. Okay. Lots of stuff with i's today, right? Okay, assignment for today. Sorry. 65 and 75 are some harder division problems, so I'm being nice. I took those two out for you. Unless you're getting a need for just, challenging yourself for something tonight, then you can do those two.